In today's video, we are going to solve two examples on the application of mathematical induction. In the first exercise, we are asked to prove by induction that if y is equal to the x multiplied by exponential of x, the nth derivative would be like this. Typically, we have 4 steps in using the induction rule. At step 0, we state the proposition clearly. In step 1, we prove that the relation is true for n equal 1. So we take the first derivative of y here. To do so, we need to use product rule first. So what is product rule? As a hint, product rule is look like this. Let's put ux as x and vx as exponential of x. So now we need to calculate the individual function's derivative. Derivative of x in respect to x is 1. So the first term would be exponential of x. To calculate derivative of vx or exponential of x, we use chain rule, which is derivative of argument x multiplied by exponential of x. Now factor out the exponential x out of the expression. We will have x plus 1 multiplied by exponential of x. So we can see that this relation is true for n equal 1. In the next step, we assume that the relation is correct for n equal 1. So k derivative of y is x plus k multiplied by exponential of x. In the last tricky step, we need to calculate the k plus 1 derivative of y. Now we just need to take a derivative of the nth derivative we just calculated from the previous step. Again, we use product rule and then chain rule to obtain the derivative of product of x plus k and exponential of x. If we factor out exponential of x, we can see the relation is correct for n equal k plus 1. So it is true for any positive integer n. As a conclusion, we can say that the result is true for n equal 1. And if it is true for n equal k, it is also true for n equal k plus 1. Therefore, the result is true for all n members of positive integer by the principle of mathematical induction. In the next example, we will see the application of the induction in the sequences. In this example, we have a sequence start with u1 equals 7 and has a recurrence relation as un plus 1 is equal to 2 multiplied by un plus 3 for any n equal or larger than 1. Prove that the general formula for the sequence is un equal to 5 multiplied by 2 to the power of 2 to the power of n minus 3. In the mathematics, a sequence is an ordered list of numbers or other elements like geometric objects that often follow a specific pattern or function. Sequences can be both finite or infinite. So here we refer to a chain of numbers that usually follow a particular pattern. They can be defined by a recurrence relation or inductive rule. You can see the description of the problem here again. Same as now, example number 1, we need to write up 4 steps in induction. At first step, we restate the proposition. In the next step, we check it for n equal 1. Substitute the n as 1 in the general formula. So the u1 is calculated to be 7. So it works for n equal 1. In the next step, we assume that it is working for n equal k. So uk is 5 multiplied by 2 to the power of k minus 3. Now we want to prove it for n equal k plus 1. So we use the relation, a recurrence relation. So uk plus 1 would be this. If we rearrange a bit and merge exponent numbers with base equal to 2, we can see that the relation is holding for n equal k plus 1. So we can conclude that the result is true for n equal k, it is also true for n equal k plus 1. Therefore, the result is true for all positive integer n by the principle of mathematical induction. What should we do if our n plus 1 term is in the sequence is the function of previous two consecutive terms? Let's work on one example. We are given a sequence with the recurrence relation u1 equal 5, u2 equal to 13, un plus 2 is 5 multiplied by un plus 1 minus 6 un for any n equal or larger than 2. We are asked to prove that the general formula for the sequence is 2 to the power of n plus 3 to the power of n. To use induction to prove it, we need to apply some changes on our general method. As before, in the first step, we restate the proposition. Now we check that relation for n equal 1 and n equal 2 is correct or not. It means we substitute n equal 1 and 2 in it to the formula, to the general formula, and then compare them with the given u1 and u2. So u1 is 5, and if we substitute n equal 2, u2 will be 13. So after doing that, we see that it is working. In the next step, we assume that the general relation is working for n equal k and n equal k plus 1. Now we need to obtain the general formula for n equal k plus 2. We use the recurrence relation. Then uk plus 1 and uk are substituted by the result from the previous step, which are shown by red color here. So we write 6 as 2 multiplied by 3 and combine 2 and 2 to the power of k and 3 with the 3 to the power of k. Then factor out the same power numbers like 2 to the power of k plus 1 and 3 to the power of k plus 1. Finally, we obtain that uk plus 2 is equal to the sum of 2 to the power of k plus 2 and 3 to the power of k plus 2. This means that our relation is working for k plus 2. So it is working for each positive integer n. Now we conclude that the formula works for n equal 1 and n equal 2, and if it works for n equal k and n equal k plus 1, then it also works for n equal k plus 2. Therefore, the formula works for all n's as member of positive integers by principle of mathematical induction. Thank you for watching the video.